Swayam Prabha. Digital India. Educated India.
Okay, so that completes my discussion of modern challenges. Let's conclude the talk. So what was the wonder element of the Fortran? The wonder element of the Fortran was that it managed the apparent conflict between expressiveness and efficiency. It brought in just about enough expressiveness without compromising on efficiency. So when we talk about efficiency, expressiveness, we're talking about efficiency of programming and the reach of programming to people. And when we talk about efficiency of program execution, we're talking about efficiency of resource utilization. So Fortran was an example of the triumph of the genius of and over the tyranny of or. Fortran managed to do it. Okay? So it was the software equivalent of a transistor. Okay, John Backus was an example of a man at the right place at the right time for the right problem. Okay. So what is the challenge ahead? The expressiveness versus efficiency conflict due to the problem of scale. This continue to exist. Earlier it was because this was not done before. Now it's, although it's been done, it's because of scale and because of new architecture features. So have we reached the von Neumann bottleneck? So John Backus argued about it over 3 decades ago. He was actually very disappointed with the Fortran compiler and sequential model. He used to say that we've reached this bottleneck. We need to design better languages and better compilers. And here's the interesting thing. At an abstract level, the status of compilers is similar to those in the John Backus era. Architectures are not understood well enough for exploitation by compilers. I gave you an example of relaxed memory consistency. And architecture influencing language features. This is exactly what happened in John Backus' time. And there's always this comparison with assembly. So you talk about embedded processors, and you still have people who will say my assembly language programs are better. You'll be surprised to know that we still have companies which employ programmers who would compile the program and then optimize the assembly program manually. There are teams which will optimize the assembly program to get the juice, the last bit of drop out of the architecture feature. So comparison with assembly, although for the standard features, for the standard processors, that doesn't exist anymore, but for the frontiers, on the frontiers of the architecture, let's say you talk about supercomputing, you talk about parallel computing, tomorrow if you talk about quantum computing, the comparison with assembly will always exist. And when it comes to comparison with assembly for such applications, there is no past success story. So the era faced by John Backus was characterized by these 4 features, and I feel that on the frontiers of computing, these 4 features continue to remain like this and continue to torment the compiler writers who try to address these features. I have listed in the many interesting references that I have used in building this talk. You can go through these and read the original text. So what is the moral of the story? The moral of the story is, let's plot on the y-axis the need of achieving performance. How much performance can you achieve? And on the x-axis, let's plot expressiveness. By expressiveness, we mean rich abstractions which enable writing concise programs with well-defined meaning, without getting into too many lower level details. So that's expressiveness. Let's also plot generality. Expressiveness, the more expressive we have, the more expressive features we have, the more general it will be. And by generality here, I also want to include retargetability, upgrades of the software, enhancements of the software, and also let's include how many guarantees can we provide, correctness, robustness, security. These are the expectations from compilers. So these are two orthogonal things, it so turns out. So the range of modern compilers goes from here to here. Either you have compilers that provide great performance, but then expressiveness goes for a toss, because they would require the programmer to annotate the program with contracts or with statements about what side effects these functions may have. So then you are ditching expressiveness. You can't even give guarantees. So very few guarantees, but very high performance. Or this whole range is this. Or you can have extremely rich thing but low performance. I mean, compilers or even interpretation for functional languages falls in this range. Of course, they're not as bad in achieving performance as what it was earlier, but compared to, let's say, highly efficient compilers, their efficiency is still much less. Okay, so the point is, the goal is getting here is the real challenge. Can we achieve performance and yet give guarantees and have expressive language? So we might keep playing on this range. So when we do things more expressive, perhaps we are not giving performance. If we want performance, perhaps we are reducing expressiveness or fewer guarantees. The more optimizations you do, the fewer guarantees that you can give about the compiler. Even now, there are people, for example, Atomic Energy Commission, they want a certified compiler because they are running a nuclear reactor, and you can't afford to have a comma being replaced by zero for a nuclear reactor. And those compilers are then non-optimizing compilers. Then we say, look, we can't give you performance if we want to give you guarantee. The current compilers that we use on the desktops or somewhere here, they give some guarantees and they give some performance as well. Okay, but the real goal would be to get here. This is the real goal that I mean, very few people even know that these challenges exist for compilers, and there is scope for doing a lot of research in compilers, but this is the real challenge which has been unmet. The whole point is, the world awaits another John Bacchus to give us the next breakthrough. We still don't have, and hopefully there will be another John Bacchus who will help us put here. And that is all that I wanted to share in my talk. I will be happy to take questions.
Hello.
Yes, Aman?
Yeah, so we can actually kind of measure performance. So are there some metrics to measure the expressiveness of a language, or
Good
do we
question.
just
Good question. No, unfortunately, there aren't any measures. There aren't any quantitative measures to measure expressiveness. There are certain design principles that people use in designing languages, but they are qualitative. We don't have quantitative measure of expressiveness. One measure could be, maybe, if all of us agree, for the same program, how much code do you have to write? I mean, are you able to write in 2 lines? Are you able to write, or do you need 200 lines? Maybe that could be one way of quantitatively measuring expressiveness. I don't know. But that's a good question. I have never thought about that uh, issue of measuring quantitatively how expressive a language is. I know I haven't answered your question satisfactorily, but that's the state of the art.
Thank you, sir. And one more question I had. So, sir,
Yes.
can you just little bit explain more on the hardware view of memory model and the languages view of memory model? One was sequential consistency, other was strong consistency.
Oh, so
So I
yeah,
was kind of
I rushed a bit. I think the story here is the following. The sequential consistency says that because there are threads running, I do not know dependence across the threads. So if you observe, so you have 1, 2, 3, 4, 5, 6. There are 6 interleavings that I have listed here. The underlying property of each of these is that the sequentiality of statements within a thread is preserved. So you always have a equal to x executing before y equal to 1. Here, here, here also, here also, here also, here also. Similarly, you always have b equal to y and x equal to 1. B is equal to y executing before x equal to 1. So the sequence within a thread is preserved. And it's called program order. So you have written things you've written the program in a sequence and you're preserving that program order. So there is a sequence between this and this, there's a sequence between this and this, but these are expressed as parallel. So there is no sequencing in this. So you might jump from here to here and from here to here, or you might jump from here to here or here, whatever, right? Whereas what the relaxed memory model says is that I will execute y equal to 1 before a is equal to x. So I am not preserving program order. Relaxed memory model allows violating program order. What is program order? Program order is a is equal to x must be executed before y is equal to 1. But this allows violating the program order. This says I will execute y equal to 1 before I will execute a equal to x. And therefore, you end up getting a result that is not preserved by sequential consistency. Does that answer your question?
Yes. So, is there any real life use case where the relaxed memory consistency will be like better? Because I'm not able to make sense. Like
Okay.
it would be really hard for the programmer.
So the point is, if there is really no dependence across the threads, then it gives the computer architecture the freedom to reorder the statements, and then the architecture can keep certain pipelines full more often than it would if you restrict it, saying that no, this has to happen in this particular sequence.
Okay.
So you can take advantage of filling the pipeline. So I don't have a particular application where this will be useful, but at the lower level, architecture can keep the pipeline full, and therefore you can expect the programs to run faster.
Okay.
That's a good question. Maybe I should include a slide on it. Where is this useful? Maybe I should note it down. Does it answer your question?
Yes, sir. Yes, it does.
Any other question?
And strong consistency is same as which one of these?
So
There was
strong
one.
consistency says that you are not supposed to interleave the threads. You will execute first thread and second thread, or second thread fully or first thread fully. So the first two examples are examples of strong consistency.
So sequential strong is same.
No. This is not strong, but is sequential.
Okay.
Right? So strong says threads can execute in any order, but within the thread, you are not allowed to.
They cannot. Okay.
Sequential
So first
says
two examples
are you can interleave. Okay, you can interleave, but within a thread, you are not allowed to reorder. Okay. And relax says within a thread also you can reorder. So look at it this way. Can you reorder threads but not interleave them? Yes, that is strong consistency. Can you interleave the threads and not reorder statements within them? That is sequential consistency. Okay. Can you do anything that you please? That is relaxed consistency. Okay.
Yeah. Thank you, sir.
Yeah. Any other question?
Sir, have you tried doing things the other way around? Like we design a very expressive and very powerful compiler, and then we make the hardware, we tailor make the hardware so that you can run this compiler specifically.
So people are trying to build hardware for streaming applications and machine learning applications.
Yeah, something like TPU, right?
I don't know the names of the architectures, but yes, there are efforts that try to address those concerns.
So
And
then,
therefore, the language design and the compiler design is important there. And in fact, nowadays, in most cases for special applications, there's this notion of hardware software co-design, where maybe I should note it down. I should go in my slides. Hardware software co-design, where you don't write a compiler after designing the architecture. You write a compiler along with it, look at the performance that the compiler gives, and accordingly decide what instructions should be supported on the architecture. So compiler development and architecture development happens in parallel. That's the dominant theme that I should have included in my slides.
yeah, that makes a lot of sense, right? Like,
Yes,
so
yes.
they'll both work with together and they'll have all
Yes,
the.
particularly for example, let's say you're working on for streaming applications or machine learning applications. Your compiler might expect a certain kind of instruction, and a compiler might expect a certain kind of feature that can be efficiently compiled. So let's get back to this picture that I had. I added this picture in the break. I want to develop on this picture. We can really play with various paths through this picture. So, and compiling techniques and architecture could happen simultaneously. So keep this picture in mind when you talk about frontiers of compiling. Okay, any other question?
Sir, I work a bit with quantum computing. So, like when you spoke about quantum computing, I thought it was really striking. It sort of struck me at that moment. So, it's like we write code in any sort of gates, but then the machine actually runs. Machines are very limited, and the topology they have is very limited. So you actually have to always break it down to a set of gates, and you always have to do that. And then we also have a set of passes called transpiler passes, just like this. So like a lot of it is very similar.
Yes, yes. So it's an example of, now you feel like you are in the John Backus era, right? You have
Yeah.
very rudimentary help available. You have an architecture that doesn't support it. So, that's what I meant, that when it comes to frontiers of computing, we are back to the same era that John Backus and people faced, and therefore we need the next John Backus.
But there, the focus is primarily on how you reduce the number of operations to the least. If you can mix them into one, by any way possible, reduce them as least as you.
Exactly. That's how you achieve performance. So I mean, this is the picture that I had in the end. Oh, yeah. So this is the picture. Anyhow, you get the performance, even if it's not very expressive. It's okay, right? So this is the range of modern compilers, right? Okay. Any other question?
I had a question. Like, since you said that GCC did not do like the loop thing, but the Photon, like in the 1980s, did the same thing. So why was this like? Why didn't GCC take it up from there, like the
Good question.
compiler?
Very good question. That's because GCC has to address a much bigger generality than the Fortran compiler had to. GCC's backend is supposed to works on close to 200 processors. So GCC is actually a framework. It's not a compiler. You generate a compiler out of that framework. So I rushed through some of the slides. Maybe I will get back to it. So GCC is a compiler generation framework. So you have some language specific code, you have language and machine independent code, and you have machine dependent generator code, and you have machine descriptions. Okay. And what you do is you actually build a compiler by giving an input language and a target language. So there is, when people work in GCC, that's the development time, then there is a build time, and this is out comes a compiler which has a parser, a gimplifier, a tree SSA optimizer, an expander, an optimizer, and recognizer. And the story is similar to LLVM, except that in LLVM you don't get a boxed code. In LLVM you have a library of all these and you can use things at will, whereas GCC doesn't create a library that you can use in your own compiler. I mean, in fact, this has been a philosophy of GCC. It has stayed with GCC for a very long time. I remember in 1997, I had an email exchange with Richard Stallman. I had freshly finished my PhD and I had worked on bidirectional data flow analysis, and there was this partial redundancy elimination, and I wanted to put that in GCC. And I observed that putting that in GCC was very hard. So I wrote to Richard Stallman, like a fresh, energetic, enthusiastic, freshly finished PhD student. I wrote to Richard Stallman that you have a great compiler, you see, but I have a great technology and I can't put it in your compiler. So can you simplify your technology, bring in a 3-address code IR? And Richard Stallman's reply was characteristic of his usual stand. He wrote me a one-line email that if we simplify the IR, it will allow other companies to use the GCC compiler backends. And he concluded by saying, we will not cooperate with any such projects. This is what he wrote to me in 1997. And then I gave up. But of course, later in the mid 2000, GCC indeed, steering committee indeed came up with a decision, and people indeed put in the Gimple representation, which is a 3-address code representation. And now we have a variant of partial redundancy elimination in GCC. So the whole point is the following. GCC has to cater to, there is a certain philosophy because of which they don't build libraries. That's one part of it. Second is, within that limitation, they have to be more general. LLVM can be more general because they let you build libraries. But by the same token, LLVM can't give you the guarantees that GCC can give you. So GCC in a strictly controlled code has to give guarantees on a host of processors. So this generality is what reduces the things that John Backus and his people did. Of course, there is still no reason why it cannot be done. But somebody would ask a question, what is really the benefit of it? And we will have to really measure how many pipeline stalls are preserved by flattening a nested loop into a singly nested loop. If that study is done, maybe some people might even do it now by writing the optimization. But that need was not perceived by GCC as something very necessary. For John Backus, that was very, very necessary. Does that answer your question?
Yes, sure. Thank you.
Yeah. Any other question?
Hi, sir. So I really like the graph at the end in which we observe that performance and expressiveness are orthogonal concerns. But we also have one more observation that Moore's law is now not giving the returns that it used to give.
Right.
So it turns out that the hardware is now not improving performance every 18 months as we used to see.
Right.
And I read this. I read this really interesting paper by Charles Lyserson and a couple of other people at MIT, in which they basically said that Moore's law is not going to give you as much performance. So we expect the next generation of performance improvements to come from above the stack. And what they basically said was that the performance will now come from the improving memory movement, improving the compilers, improving the system software.
Right.
So
yeah, they are the creators of Silk programming language.
Yeah, exactly. So
yes.
where do you see, I mean, in light of the death of Moore's law, where do you see, what is the role of compilers in the next decade?
That is the reason, that's the biggest reason why I say that the compilers face the same challenge as, the hardware view. Hardware is trying to beat Moore's law by bringing in all these things.
Exactly.
And many core compilers, you still don't have very good compilers generating code for many core processors. So
Yes.
that's the challenge. And it is in this sense that in my conclusion, I said these four statements. These architectures, the new architectures, they're not understood well enough in the sense of in the sense of their semantics. For example, I took relaxed memory consistency as an example. So they don't have formal guarantees. They work very fast. So how do compilers exploit it? That's a challenge. So architectures are influencing language features. So that's exactly why I said that, in fact, this graph recognizes the fact that the architectures are becoming different from what they were. And that is why compilers can't achieve performance without getting rid of expressiveness. At this end, you can imagine that, you simply write assembly language program, and at this end you write a very high level language program. So I think that's what, so this chart actually shows that because architecture, so the reason why we are unable to achieve performance with expressiveness is because the architectures are crazier. That as soon as we understand some features of architecture, we have people coming up with a new set of features. So that's the reason why I drew this graph this way.
Yeah. Yes. Actually, so this brings me to this question. So I do a bit of research in architecture, and in architecture, we have this huge push towards domain-specific architectures and ASICs right now. I
Right.
mean,
Right.
conferences like ISCA, ASPLOS, they're filled with these proposals for specialized architectures. And now that I see the compiler's perspective of it, it all just falls apart because these ASICs are completely useless if you cannot program for them.
Absolutely. Absolutely. So that's the challenge that compilers are facing. And that's the viewpoint that I want to bring out. I mean, very few people, first of all, very few colleges teach a compiler course. And when they teach a compiler course, they teach you just the standard stuff, and you get an impression that compilers exist for everything. So what do compiler people do? I mean, I have had trouble explaining people that I'm doing research in compilers, and I'm busy. I'm very happily busy for 30 years. They say, what are you doing? Everything is done already.
Exactly, sir. Exactly. That is that is what people say. Exactly.
So
Yeah,
this talk
completely.
has come out of because of that. Of course, the motivation was that there was this Turing centenary celebrations, and John Backus is one of the Turing awardees, and they wanted someone to speak on the work of John Backus, and that's where the this talk arose.
Hmm. Yeah. No, I mean, yeah, I think you mentioned that polemic by Rob Pike, and I also read that. And in that, he also mentioned this thing called as Probsting's law, in which compiler performance doubles every 16 or 18 years.
Yes, yes, yes.
Yeah, I don't know because this is an extremely important technology, but I don't understand how it's going to evolve in the next decade.
Yeah. So I have written down some papers. Something called "Is Code Optimization Research Relevant?" Bill
Yes,
Pooks
yes.
had this talk in 2000, and then is the death of optimizing compilers. Daniel Bernstein predicted that in 2015, and then there's Lawrence Stratt. I think you mentioned about it. What challenges and trade-offs do optimizing compilers face? So I think these are worthwhile readings for the big picture. Yeah.